About reinforcement learning. Imagine a robot learning to navigate a maze. Reinforcement learning allows the robot to learn by interacting with the environment. It receives reward for desired action and penalties for undesired action. This reinforcement is fully based on training a model by giving a point, positive point and negative point to it. The goal for the robot is to learn the best course of action to maximize the long term rewards. Here we will consider some of the key points. First one is agent. Our robo friend constantly learning and interacting with the environment. Here, environment, the maze providing reward and feedback based on the agent's action. State, the state represents the robot's current position and sensor reading within the maze. Action, the robot's choice, like moving forward, turning left or right. Reward, the reward is a feedback signal, a positive reward for getting closer to the goal and negative reward for hitting walls. This is the most important key player concept involved in the reinforcement learning for maze game. There are different types of reinforcement learning, each with its approach. First is model based. The robot tries to build a mental map of the maze to predict future rewards, like studying a map before entering the maze. Next one is model free. The robot learns differently from experience, like trial and error exploration within the maze. And another model is on policy versus off policy. In on policy, focus on the current strategy the robot is using to learn, whereas the off policy lets the robot learn from the past experience even if they were from different strategies. These are the some of the models which is used to learn the or train the model. And some of the popular reinforcement learning algorithms are given here. That is Q learning. In Q learning, this one helps the robot estimate the value of taking an action in a specific state. It's like the robot learning which paths are more rewarding in the maze. Next one is deep Q networking. Imagine the maze is massive and complex. Deep Q networking uses deep learning to handle these situation, making the robot a super maze solver. Next one is proximal policy optimization. This algorithm tackles challenges in on policy learning, ensuring the robot's learning process is stable and avoids getting stuck. We will see some of the example or application of reinforcement learning. First one is robotics and automation. In robotics and automation, reinforcement learning can help the robot learn complete complex tasks like grasping objects, navigating obstacles, and adapting to changing environment. In warehouse automation, reinforcement learning can optimize the movement of robots and drones in warehouses, improving efficiency and throughput. Next, reinforcement learning plays a role in games and entertainment. In games, playing games, reinforcement learning agent have achieved superhuman performance in complex games like Go and StarCraft 2, surpassing the best human player. And non-player characters plays like reinforcement learning can create more dynamic and challenging modes in video games. making them more realistic and engaging opponents. It is reinforcement learning is also involved in finance and trading, where a reinforcement learning agent can analyze market data and making trading decision in real time, potentially outperforming traditional algorithm. And in management, reinforcement learning can use to develop strategies for managing financial risk and making better investment decisions. And more, there are more applications for reinforcement learning. Reinforcement learning algorithms are open doors to incredible possibilities. From training robots in complex environment to mastering video games, these algorithms are pushing the boundaries of what machine learning machines can learn.